In this module, we're going to take a look at microarchitecture exploitation. Now that's a mouthful to say, so what is microarchitecture exploitation? Well, if we look at kind of the caption of this particular lecture, it's captioned below assembly. Why below assembly? Well, let's think back to kind of our beginning of understanding how vulnerabilities work. We could look at a higher level programming language like C, and we may be able to identify logic bugs that exist because a programmer made a mistake and they wrote the wrong C code. But there's a lot of vulnerabilities, exploits, and bugs that aren't immediately apparent when you're thinking in a higher level abstraction like the C programming language. And so what we as the attacker got into the habit of doing was thinking about what is going on at a lower level abstraction than the people who are writing the programs. And so we started looking at the assembly instructions that are running on the CPU. And once we had a good understanding of what is going on in assembly and in the CPU, we could discover a class of vulnerabilities, for instance, ROP or buffer overflows, that we didn't necessarily know about when we were thinking in a higher level programming language, because the concepts that were necessary to understand these vulnerabilities simply weren't there in a higher level abstraction. Microarchitecture exploitation is going one layer lower. So there's a lot of implicit assumptions that we have about how our program runs. We had some assumptions about how our program runs in C, and we could find things that were not true about that once we were looking at how our program operated at a lower level in the assembly. And so now we have some assumptions about how our program behaves in assembly that is running on the CPU. So how do we go lower than the assembly? The assembly is the lowest version of the actual code that is the program. Well, the answer is we go into the behavior of the hardware itself and a discussion of exploits that implicitly exist in the hardware that is running the code. That is microarchitecture exploitation. So let's look at kind of one of the assumptions that we've implicitly had when we think about assembly running on the CPU. If we have an assembly instruction like this, which says move RAX plus 20 into RAX, what is occurring? Well, we're dereferencing some virtual memory address. In this case, whatever happens to be RAX plus hex 20. Now that virtual memory address corresponds to somewhere in RAM, in memory. Now, if you think about the hardware components of your computer and where they physically exist on your computer, the assembly instruction is running on your CPU, and that's on one side of your motherboard. Now, the memory that needs to get accessed is in the RAM. And so the time that it takes for the electrons, for that data, that request to go out and reach the RAM, and for the value to get found and the value to get returned back to the CPU is forever compared to a CPU cycle time. And so when we think about, okay, well, we're going to perform this instruction, what is the CPU doing during that time? Logically, we kind of think about it as if the CPU is just kind of sitting there and waiting, and it's just waiting for the RAM. And at one point in time, that was probably a thing. But nowadays, in modern CPUs, this isn't the case. So what is happening inside of a modern CPU when a request to go access some memory address occurs? Well, the answer is the RAM may not actually get accessed at all. So this instruction implicitly, we think about it, and it's not incorrect to think about it this way, but we think about it as if every time we see a dereference of a virtual memory address, we're going out and grabbing some value in memory and then moving that into a register that exists in the CPU. But in truth, there's a caching layer, and this caching layer may cause this instruction to not actually touch RAM at all. And so instead, what could be occurring with this same instruction, this is how we think about it, right? The virtual memory address translates to somewhere in the physical RAM, which then gets accessed, the value gets pulled, gets passed into the CPU, and then gets moved into the RAX register. But there's actually caching layers. And so if this memory address has been accessed in the past, instead of going all the way across your motherboard to the RAM, and even if these are physically near each other on your motherboard, in the scale of electrons, it is a massive distance. So don't hold me to the other side of your motherboard here. But there is a caching layer, a layer of a super fast, super local memory that is inside the CPU. And there's typically multiple layers of cache, but we can treat it right now as one layer of cache. And so if that CPU or if that core has accessed that memory address recently, it's going to keep an entry of what the data is in the cache. So if it needs to get accessed again, we don't have to waste that time going out and touching RAM again. And this is actually something that we can not directly see, but it is something where we can observe the side effects of. And so I have a demo here that we'll take a look at where I claim I can show you whether or not the cache was hit, or if we took the long way around and grabbed a value all the way from the RAM. So let's take a look at that. Okay, so if we take a look here on the left-hand side, I have a C program. I'm going to run through it real quick. But one thing that is worth noting is I have these kind of new magic functions that we haven't seen before. We have mmcl flush, I have mmfence, and I have rdtsc. And these functions are coming from this x86 intrin header file. This is shorthand for x86 intrinsic. This header file allows us to interact with some of the CPU behaviors or encourage certain CPU behaviors. Now, that doesn't mean that I can directly access the cache and show you what is in the CPU cache. But what I can do is I can influence the CPU in a certain way so that we may be able to observe side effects that are a result of a value being in the cache or in RAM. Because remember, if it's in the cache, this is really quick to grab the value. And then if it is in RAM, it's a long trip. And so it will take a long time to get the value. Now, what I've done here is I've commented above kind of all of these magic functions as far as what they are doing at a high level. So let's run through this here. The first thing that's happening is I'm setting this buffer array, which is an 8-byte character array. I'm zeroing all the values in it. The next thing that I say I'm doing is I'm flushing all buffer memory from the cache. Now, the first thing you'd be thinking is, whoa, wait a minute here. How do I even know this is in the cache? And the answer is, I don't. I have no knowledge about what is in the cache at this point when this program starts. So why am I flushing something? Well, I need to enter a known state. Now, the act of flushing something from the cache that isn't in the cache is essentially a no-op. I didn't impact anything, but I know after this flush that the buffer value is not in the CPU cache. So what do I do next? Well, I'm going to set a high resolution start time. This is kind of like calling get time. I'm getting a super high resolution counter from the CPU itself here. Now I'm going to access a value from buffer. Now this looks pretty weird because I'm calling buffer and I'm accessing it via buffer. Note this weird pattern I have going on here. I'm not going to go into why, but this is necessary. Just know that this is accessing the buffer value, and we're putting it in X. I'm not printing X. I'm then going to get an end time. So I start a time, I access this value, I end time, and I'm going to calculate how long did it take for me to access this virtual memory address and put it in X. You'll also note that X is volatile. This is necessary to prevent compiler optimizations because the compiler will try and outsmart you. It will say, well, you're storing a value in X, but you don't use X anywhere, so maybe we can remove that. By making this variable volatile, I'm preventing the compiler from compiling this to assembly that is drastically different than this high-level C code. And I'm going to print off how long this access took. if we look directly below there, I've kind of sectioned this off. So the upper part is the first access. In between here, I have CL flush, and I claim that I'm flushing the cache between accesses. This is, in fact, the same instruction that we have up here, where I'm calling mmcl flush on the buffer. Down below, on the third kind of part of this program, I'm doing the exact same access pattern again. So I'm starting a timer, I'm accessing this buffer and putting it in X via the exact same mechanism here that's just kind of strange. I'm then getting a high resolution time again, and I am printing out the access time for this second access. So let's compile this. So far, so good. And let's run it. And what we see here is the access times, while they do vary, there's not really a clear pattern here. So most of the time it looks like the second access happens to take a bit longer. But if we look here, the first access took longer. But yeah, I mean, they're roughly occurring at the same number of cycles, right? They're taking the same amount of time. And that makes some sense because right here, I'm flushing the cache. So I'm preventing the cache from like influencing this really at all. Well, what happens if I don't flush the cache? So it's the only change that I'm making is not flushing the cache between these two accesses. Now I run it, and we see access 2 was quicker than access 1. Okay. Well, now it's considerably faster, and we see that this pattern holds. And in some instances, it's almost twice as fast to access this same location the second time. This is happening because of the cache. And so we can observe the time impact of a memory address existing in the cache. The low time values are when we're accessing the cache. But if it's not in the cache, which is what we see here for the first access, it's going to go out to RAM, and that takes a long time. So what other assumptions about the behavior of assembly on the CPU do we have? Well, one of the things that we've assumed is that instructions are accessed in order, and RAP is always pointing to the next assembly instruction that's about to be executed. And this makes sense in like the way that we think about how programs execute. But I've already said that accessing RAM is really slow. So is the CPU just going to sit there and wait for this RAM value to get accessed and returned to it into a register? Couldn't the CPU be doing something with its time? So like if we look at this, which is just an extension of that initial access here, well, we said accessing RAX plus hex 20 may have to go all the way out to RAM, and this could be a slow operation. So what if instead of waiting for that, the CPU did something useful? Well, what could it do? Well, let's look at the next couple instructions. We need to compare RAX, which I can't do because I need to access the value from memory. Based upon that value, I'm going to jump to label, or I'm going to not jump to label. In either case, what I'm doing is I am moving a value from RDI to this other memory address. So what could the CPU do with its time? Well, the answer is it can speculate while waiting for other components. Typically, memory access is kind of the one that causes this. The CPU will speculate. And so instead of waiting up here, what's slow, is the CPU will just say, okay, well, the only thing I care about is RAX 0? And it'll be, okay, well, we'll assume RAX is 0. So then if we assume RAX is 0 up here while we're waiting for the memory, we'll compare RAX with 0. Well, then if we assume that, do we jump to the label? Yes, because we assumed RAX is 0. And so then we are right here, and we're about to write the value of RDI, which is 0 based upon our assumptions, to this memory address. And this is speculation, where we guess a branch that is going to be taken. We are waiting for memory and we just say, okay, well, what if it's this? And if we're incorrect, if we go here and it turned out that RAX was not 0, well, then we'll just undo that because we were doing nothing with our time anyways. And so there isn't a loss to guessing and being wrong. In the worst case scenario, we guess, we're wrong, and then once we have the correct value, we just go backwards in time and start over based upon the correct information. But if we're right 50% of the time, right? Let's say it's 50-50, whether or not our guess is correct. Half of the time, we have gained a massive performance improvement not waiting for this memory access. The other half of the time, there may be a slight loss in performance from like rolling back, but we could be clever about how we do this rollback or reset in the event that we're wrong. And so we'll assume that that rollback is free. And so spending our time that would be waiting, guessing, and then being right half the time is actually a massive performance improvement for the CPU. And so this is what's known as speculation or speculative execution. And so while waiting on other components, the CPU will guess a branch to be taken if we don't know the value because we're waiting on memory. If it's incorrect, then we'll redo the calculation from the branch. We'll go down the other path. But if it is correct, I've already done the work. The CPU's already done the work, and so it can continue ahead, and it gets a head start on execution. Now, this occurs in the CPU hardware. However, it can be detected. I don't have a good demo that just clearly demonstrates speculative execution. However, there are some exploits that we'll be talking about in later lectures that utilize speculative execution, where we can prove that it is in fact occurring via the exploit itself. So the exact behavior as far as speculation and the exact behavior as far as cache varies from CPU to CPU. It can vary based upon the vendor. It varies based upon the model. It is very specific to the exact CPU that is in your computer. Additionally, there are OS security features that may enable or disable different speculation features or different caching features or ways that the cache layer is being used. And so you can see different behavior in kind of this lower level below assembly based upon these factors. If you are interested in kind of seeing what this looks like or what is going on with a particular CPU, these are two commands that can produce output here to give you information about your CPU. So let's take a look at that here on the Dojo. If I cat proc CPU info, we see there is a ton of output. The CPU that is running the Dojo has many a core. And so the CPU info output shows us all of the cores and hardware threads that exist within the CPU. Additionally, there's actually more than one physical CPU, which makes this output even more interesting, which is why we have a physical ID that can be 1 or, I believe, 0. See if I find it here real quick. Yes. And that is the physical CPU. So there's the physical CPU, then there's the core, then there is the hardware thread. Another value that is worth talking about is every CPU has this CL flush size. This is the size of a cache entry, right, or a cache line, if you will. And so when I flush something from the cache, I am flushing 64 bytes. And we see that the cache is aligned to 64 bytes. So if I access something at hex 1000, what is going to go into the cache is hex 1000 to hex 1064. That is the bytes that would get loaded into the cache as a single cache entry for this CPU, because the cache size is 64 bytes. So what is the problem here? What is the problem with these features, right? These sound like great things. Caching makes our memory access faster, and speculative execution here, we've said, makes executing faster. And it's essentially a free performance win in both cases. Well, it turns out in 2017, there was a series of papers that were published that kind of brought vulnerabilities that exist in these mechanisms into the light. And there were two kind of dominant methods here. One is known as Spectre. The other is known as Meltdown. Later in this module, we're going to discuss how Spectre and Meltdown work. And so we'll look at how these caching mechanisms and speculating mechanisms can be abused to provide an exploitation primitive. Both of these have great research papers that are worth a read if you want to get into the nitty-gritty. Well, these CPU performance optimizations occur in the hardware, right? And so if there is a hypothetical vulnerability, what do we do about that? If there's a vulnerability in a C program, we can fix our C program. We could patch it. We could update it. If there's a vulnerability in a binary and I can't recompile it, I could edit the bytes that are the assembly in the binary if I had to. I could rewrite the assembly, right? We can change the program. But what do you do if there is a problem that is in the hardware? Now, I say here that this is visibility into these optimizations, provide a new side channel. What does that mean? Well, if you think back to the baby jail module, a side channel was where we could convey information by like unconventional means. And I said earlier here that we could determine whether or not something was cached based upon the length of time it takes to access it, doing something like this, right? I could determine if a value was in the cache. Now, this happens to be in one program. And so you're like, okay, Robert, what's the big deal? You're just finding out how long it takes you to access a particular value. But remember that when I am putting something into the cache via accessing it, that isn't the cache for this program. That is the cache that physically exists for the CPU. And so if you have multiple programs that are accessing the same shared memory, the same underlying page, then you can determine whether or not that value was accessed across processes or across user space or across, well, there's a number of different ways, but basically anything that can access the exact same memory address. Kind of the simple, straightforward example to understand is if the accesses are occurring in the same process. But remember, the caching layer is in the CPU, not in the program. And this is where this issue kind of exists as far as what is the problem. Well, the problem is that one program can know if another program put a value in the cache by cleverly writing a program that accesses and times these accesses. And so this provides a new side channel that wasn't there before. And this is a side channel that we can't close by patching our program. The side channel exists below the program. It's not in the C code. It exists below the root user. It doesn't matter if it's the root user or it's the hacker user. We are talking about the hardware behavior. I can't change that. It's physical. This is below the kernel. It doesn't matter if I'm in supervisor mode or I'm in ring 0. The kernel can't change the physical architecture of the CPU. And so these vulnerabilities or these side channels exist in the CPU itself. And that means that if there is a vulnerability, it is something that simply cannot be fixed in some cases. So this is the output of a command called lstopo for this particular Linux box that I run. And we see this gives us kind of a diagram of these cache layers. Now, I said there's more than one cache layer, and we can see that. So this right here, L0, is a physical core when we think about cores, right? Now, one of the things that exist in modern CPUs is hyperthreading. Hyperthreading is having more than one hardware thread on a physical core. And so right here, I see 2 hardware threads on one physical core. And if we look up this diagram, this right here, these are L1 caches. These are the closest to the CPU and the fastest accesses. Then I have an L2 cache. We'll notice that the size of the L2 cache is significantly larger than the L1 cache. And then we have an L3 cache. And this L3 cache is shared across cores. And we need to be aware of not only what is the behavior of the specific CPU, right? What is, for instance, the cache entry size? But we also need to be aware of where are these caches? What are they shared between? Because if I'm trying to perform a side channel, for instance, using this L2 cache, I would only be able to observe whether or not a value is in this particular L2 cache if the programs, the victim and the second program, the 2 programs that are accessing memory, they both need to be touching and going through this L2 cache. So I would need both programs to be running on this core. It wouldn't necessarily matter which thread or which hardware thread the programs are running on. But if I'm trying to create contention where we can observe L2 cache effects across programs, I need to make sure that the programs are in fact using the same cache. And so we'll look at ways that we can cause a program to run on a particular core to encourage these kind of interactions. As far as kind of these microarchitecture vulnerabilities, broadly speaking, this is a diagram of kind of what is in a modern CPU. Now, the picture itself here is not interactive, but if you go to this website here in the lower left, this is where the diagram was taken from. It is interactive. You can mouse your pointer over these different components. For instance, right here, we see there is a branch target buffer, right? And this is part of the branch prediction unit. When we talk about speculating, how does the CPU decide what branch we're going to take? Well, there's actually a hardware component in most CPUs nowadays that its function is to try and predict the most likely branch that will occur. And so if you can influence this branch prediction unit, then you can influence the behavior of this speculation that is completely invisible to us as mere users of the CPU, right? That this is something that's completely hidden from us. And that is just by modifying the behavior of this component. And so there are papers and exploits that exist for all sorts of components inside of the CPU. But in this module, what we are going to focus on is Spectre, Meltdown, and some of the kind of related primitive attacks, how they work, because these are kind of the big name, big news attacks. And we'll see that in the next module.